Hello everyone, I'm Sara Salem. I'm working as a Research Council Officer, RF System Engineer with the Millimeter Instrumentation Group at NRC, Herzberg Astronomy and Astrophysics Research Center. Today I'm going to present the design and analysis of three different feed horns at Q-band frequency range. First, I will give you a brief introduction and then I will explain the design and performance of a choke ring feed horn, a quad-ridge feed horn, and also a regular corrugated feed horn. I will explain various aspects of each antenna like gain, cross-polarization, side lobe level, pattern symmetry, and directivity. And at the end, I will summarize the talk and present a table that makes a comparison between these three feed horns. Horn antennas are commonly used in a variety of applications across microwave and millimeter wave spectrum, including satellite tracking, reflector feeds, measurements, and electromagnetic compatibility testing. They have many attractive features such as high gain and directivity, low VSWR, easy excitation, relatively simple construction, and high peak power handling capability. One of the most important features of the horn antenna, which makes it a popular candidate for different applications, is having full control over its performance characteristics. Ridged waveguides are adapted to feed horn structure to extend the bandwidth by decreasing the cutoff frequency of the dominant mode. Corrugations are applied for symmetric pattern, low crosswalk, high gain, and consequently low spillover on reflector antennas. An ideal feed horn should meet some important specifications like equal beamwidth in E and H plane, low cross polarization, adequate gain, low side lobe levels, and the maximum efficiency. The objective of this presentation is to design and investigate various dual polarized feed horns with low side lobe level, bore side gain higher than 10 dBi, and low cross polarization over a wide bandwidth as possible candidate as feeds for reflector antennas at Q-band frequency range. All presented antennas are modeled and optimized using CST Microwave Studio, 3D modeling, and also Visual Basic Programming in macros. The circular waveguide input is a 7.24 mm for all cases with a TE11 cutoff frequency at 24.2 GHz and TM11 cutoff frequency at 50.5 GHz to be able to cover the entire Q-band frequency range. Corrugated horns are used as improved feeds for reflector antennas and also as direct radiators for wideband measurements. Corrugated horns can produce radiation pattern having extremely good axial symmetry, relatively constant beam width as a function of frequency, high beam efficiency, low cross polarization level, very low side lobes and back lobes, good return loss, and relatively the same phase center in all cut planes containing the antenna's bore side. A nearly linear aperture electric field is the requirement for producing a symmetrical main beam with a low cross polarization level in the horns. The corrugations in a waveguide or an antenna produce a nearly linear aperture electric field of a hybrid mode which cannot be produced by waveguides supporting only pure TE or only pure TM modes. The corrugated wall can generate a condition in which both the impedance and admittance at the surface of the corrugations become zero. This boundary condition can support the propagation of so-called balanced hybrid mode HE11. To obtain good performance from the corrugations, the following tips should be considered. First, there should be enough corrugations per wavelength to have zero tangential transverse electric field at the surface of the corrugations. The corrugations should be narrow and a quarter of wavelength deep. The corrugation acts as a transmission line that transforms a short circuit at the end of the slots into an open circuit at the corrugation's boundary, causing a relatively zero tangential transverse magnetic field at this boundary. A slot depth less than a quarter of wavelength generates positive reactance like inductive and result in propagation of EH11 mode, which is a surface wave mode, and we would like to avoid that. A very gradual change from a slot depth of half a wavelength to quarter of the wavelength from the throat towards the aperture can also avoid the excitation of EH11 mode. Now let's start with our first design, which is a choke ring feed. The proposed feed comprises of a circular waveguide which excites the TE11 dominant mode in the input, and 10 narrow corrugations with a quarter of wavelength depth to achieve constant beam width over the frequency range. The aperture diameter is about 40 mm and length of the antenna is 14 mm. As it is shown, this antenna has a reflection coefficient better than 10 dB from 28 to 51 GHz and better than 20 dB return loss from 33 to 51 GHz, which covers the entire Q-band frequency range. This antenna is designed to match the dish verification antenna number 2 in Penticton, BC, Canada. The DVA2 specifications matches the NGVLA proposed dish. Therefore, this antenna can be considered as a potential candidate for NGVLA band 5 as well. Here you can see the 3 dB, 12 dB, and 16 dB beam width of the proposed antenna. For normal unshaped reflectors, a Gaussian beam has its maximum aperture efficiency when the edge taper is 12 dB. So what we do often is find the half angle of the telescope and then find the Gaussian beam that has optimum efficiency for that half angle, and after that we design a feed horn to match that Gaussian beam. So a rule of thumb as a starting point is 12 dB edge taper for half an angle of telescope. However, for shaped optics, experts are claiming that the maximum efficiency for the shaped reflector can be achieved in a different level. For example, for DVA2, it was calculated that the 16 dB taper angle provides the maximum efficiency. As it is shown, the 3 dB angular beam width is around 58 degrees with less than 5 degree variations across each axial cut. And 16 dB taper angle provides about 110 degree beam width, which matches the DVA2 dish. Another important feature of the feed horn is the side lobe level. We normally try to keep them below 20 dB. Of course, the lower the better. For the proposed design, we optimized the structure for side lobe lower than 25 dB from 28 to 50 GHz, which was successfully achieved in the different cut planes. Side lobe levels are smaller than minus 35 dB between 33 to 50 GHz. The low side lobe level is due to the ability of the feed horn shape to convert the HE11 mode into a Gaussian cross section across the aperture. As it is shown here, an excellent symmetry within half beam angle of minus 55 degrees to 55 degrees happens between the E-plane and H-plane and D-plane of far field patterns of this antenna, which is shown on the right side. And also the cross polarization is less than minus 22 dB in the entire frequency band. Okay, let's have a look on the gain. The gain of the proposed choke ring antenna is plotted versus frequency. As demonstrated here, this antenna provides an average gain of 11.7 dBi through the bandwidth. The last but not least feature is the aperture efficiency of the feed horn that we analyzed here. including this calculation includes spillover efficiency, cross-polarization efficiency, amplitude efficiency, and phase efficiency, and then the antenna was optimized accordingly to provide the maximum efficiency. This table presents the calculated aperture efficiency at 55-degree half beam width at 16 dB taper angle. It is shown that total aperture efficiency is higher than 78% in the entire frequency band. Working towards the future, we started to work on designing octave bandwidth horns with the idea of combining band 4 and 5 of the NGVLA. So far, a corrugated feed horn with a ring-loaded slots is designed. This feed horn covers a frequency range of 25 to 50 GHz with return loss better than -12 dB in the entire bandwidth. It also provides an aperture efficiency better than 79% with symmetric radiation pattern and very low cross-polarization in all planes. The next antenna is the quad-ridge feed horn. The quad-ridge horn antenna are well known for their wideband characteristics and dual polarization. They usually come as conical, pyramidal, and diagonal designs with straight and elliptically shaped walls. Quad-ridge waveguides are those which have 4 ridges loaded symmetrically in a square, diagonal, circular, or shaped cross-section. A quad-ridge waveguide supports a fundamental propagation mode polarized in either of 2 orthogonal directions, which in turn supports a mode in virtually any polarization, like left-hand circular, right-hand circular, slant linear, dual linear polarization. Ridges are used on horn antennas to lower the cutoff frequency of the dominant waveguide mode and to extend the operating bandwidth. Additionally, by controlling the ridge taper across the length of the horn, the field distribution at the horn aperture can be specifically designed for. Elliptically shaped sidewall compared to the straight sidewall improve the quad-ridge horn radiation pattern and bandwidth and make it a suitable candidate for radio astronomy applications. Therefore, an exponential taper and blending fillet for minimizing the half-power beamwidth variations while providing a high bore-side gain is designed for Q-band frequency, covering more than an octave bandwidth with return loss better than 20 dB from 20 to 55 GHz. Parameters in flare section mainly determine the radiation characteristics of the antenna. The most effective control over the beamwidth could be obtained by manipulating the profile of the elliptically shaped horn section. The elliptical shape of the antenna was modified by changing the ratio between the length of the horn and the width of the aperture in this design. The differences between the E and H plane beamwidths are smaller for the shaped sidewalls than for the conventional straight sidewalls. The shaped sidewalls also improve the rotational symmetry of the radiation pattern for the conical and pyramidal horns. As it is shown, the beamwidth performance requires more optimization to achieve the variation less than 5 to 10 degree in the bandwidth. Here is the cross-polarization performance of the quad-ridge antenna. The cross-polarization is shown only in the 45-degree plane as it tends to have the maximum there. Cross-pol has a variation between 13 dB to 16.5 dB through the bandwidth, which shows further optimizations for improving the cross-polarization is necessary. The gain of the proposed feed is plotted versus frequency here. As it is shown, it provides minimum of 11 dBi and maximum of 15 dBi gain through the bandwidth. Here is the aperture efficiency calculation for the proposed quad-ridge horn, which provides a minimum of 50% and a maximum of 69% aperture efficiency. And on the top figure, you can see the radiation pattern of the quad-ridge feed horn in different cuts. Now let's talk about the corrugated feed horn. As illustrated in figure, it is usual for the corrugated horn to be connected to a circular input waveguide. The fundamental mode of this guide is TE11 mode, and there is the need for a so-called mode converter at the transition between the smooth wall input waveguide and the body of the corrugated horn. This mode converter is designed to provide a smooth transition from the TE11 to the HE11 mode supported by the corrugated horn. For a standard application, the hybrid mode in a well-designed feed results a radiation pattern which is very close to a Gaussian shaped pattern. It is the Gaussian pattern characteristics that we wish to maintain over the operating bandwidth of the horn, in order to satisfy the cross-polarization, return loss, and side lobe requirements for the given application. Here the 3 dB and 12 dB beamwidth of the corrugated horn are presented. As it is shown, the 3 dB beamwidth has less than 4 degree variation in E and H planes. 12 dB beamwidth also has a smooth transition over the entire bandwidth from 26 to 50 GHz. The beamwidth variation and efficiency is actually way better in a narrower bandwidth, like from 33 to 50 GHz, which still covers the entire Q-band frequency range. To explore the pattern symmetry over the bandwidth, the antenna radiation pattern in 8 frequencies from 26 to 50 GHz is demonstrated in the top figure. On the right side, we plot 3 different cuts of a single frequency radiation pattern. As it is shown, there is a great symmetry between E, H, and D planes. On the bottom, the simulation results of the side lobe level through the bandwidth is plotted, which indicates that the horn antenna has a side lobe level smaller than minus 22 dB from 26 to 50 GHz and smaller than 29 dB in the Q-band frequency range. The proposed corrugated feed provides an acceptable cross-polarization through the bandwidth with room for further optimization. The cross-polarization is better than 21.2 dB through the Q-band frequency range. The gain performance of the antenna is plotted versus frequency here. The proposed corrugated feed provides a fairly high gain through the bandwidth as it is shown in the figure on the right side. Here is the aperture efficiency calculations. The corrugated horn provides an aperture efficiency with minimum of 65% and maximum of 80% in the bandwidth. As it is shown in the table, a spillover efficiency and amplitude efficiency needs to be optimized to maximize the aperture efficiency through the bandwidth. Phase efficiency can also be improved in higher frequency range. To conclude this presentation, this table demonstrates a comparison between 3 proposed feed horns at Q-band frequency range. The proposed choke ring antenna is an excellent candidate for a wide 50 to 60 degree sub-reflector opening half angle like next generation very large array reflectors. It has a symmetric pattern with very low cross-polarization, which makes it an excellent candidate. The octave band horn can also be considered as a good candidate for NGVLA dish. The quad-ridge feed can be used for octave or multi-octave band applications. It requires some minor design modification and optimization to fit in the feed horn requirement for radio astronomy applications. The corrugated horn has less than 5 degree variation between E and H planes beamwidth with minimum gain of 16 and maximum gain of 21 dBi, which makes it a good choice for narrower beamwidth application like ALMA reflectors. Thank you very much for your time and attention. I would be happy to answer your question.